These are the first real problems that we're going to be dealing with forces, and we have four examples. And so I'm just going to go ahead and start explaining how to do these. So problem number one, it says Otis sleeps. Otis is the cat that we've seen in other problems. Otis has a mass of 6 kilograms, and Otis is just sleeping on the floor. We have three questions. Question A is, oh, it's not a question. It says draw a free body diagram, so we abbreviated it as FBD. And in a previous lesson, we talked about free body diagrams. So if you're not sure what that is, you should really come see me for tutorials and talk about that, or watch a video if I do have a video on free body diagrams. Um, so we want to draw a free body diagram for Otis the cat. And so the way we do that is we draw a dot or a box. I think I'll choose a box. And we draw all the forces that are acting on Otis. And the first one you should think about is a gravitational force. And remember that the arrows must be connected. And we don't want to label it as Fg for gravitational force. We want to use mg because that's what Fg is equal to. And it's a much more useful way to label the gravitational force. Now, if that was the only force on Otis the cat, Otis would be in free fall. And so Otis would be falling and gaining speed. And so there is another force on Otis, and it is coming from the floor. The floor is pushing back up against Otis, and you can pause and think about what kind of force that is. A surface puts two kinds of forces on objects, and one of them is friction, but that's not this case. The other one is a normal force. So capital F, capital N as a subscript. Cool, so that's part A. Now that we have both forces labeled on the free body diagram, the next question is how much is the normal force? What's the magnitude of the normal force? And so for part B, we need Newton's second law, which is sum of all forces equals ma. And we are going to solve this equation. We need to start. We need to make the equation first. I mean, that's the equation, but we need to substitute these forces into that equation. Let's start on the right side of the equation. This is mass of Otis times acceleration. But we should ask ourselves, is Otis accelerating? Right? Otis is just sleeping, so clearly Otis is not accelerating. So m times 0 is just 0, and so we're going to replace it like that. All we need to do now is we're going to substitute the forces that are relevant here, and normally the bigger force should go first, but in this case, since neither force is larger than the other, they're equal magnitude, it doesn't matter which one goes first, but I'm going to say Fn first. Now, should we add mg or should we subtract mg? And we should subtract them. We should subtract mg. When they're in opposite directions, we should subtract. When they're in the same direction, we can add. Okay, so again, we're trying to figure out Fn, so we should isolate it. We're going to add it, we're going to add mg to both sides. So we get Fn equals mg. And all we need to do now is substitute. The mass of Otis is 6, g is 10, and so that's 60. The units are newtons. All forces are in newtons. Okay. You sometimes want to check and just say, okay, this is 60 newtons, mg is 60 newtons, and so they cancel each other out. There is no net force on Otis, and so Otis is remaining at rest, which is correct. So that's A and B. Question C is identify a third law pair of forces. So you might need to go back and check Newton's third law. It says when one object puts a force on a second object, the second object simultaneously exerts a force equal in magnitude but opposite in direction on the first object. Now, you might be looking at the free body diagram and noticing that these are both equal and opposite direction forces, but the free body diagram is not an example of Newton's third law. Newton's third law is better stated as a sentence. We need two objects. We can say Otis and the floor. Otis pushes down or downward on the floor. And we can say the floor pushes upward on Otis. Cool. And there we go. Whenever you're making these statements, you always want to have two objects. And you also want to show which direction those objects are pushing on the other one. And it's a perfectly good statement, perfectly good third law pair of forces. Let's keep going. You can pause anytime. Number 2, Otis sleeps in an elevator. So we just draw Otis in an elevator in a box. Oh, and by the way, the elevator is accelerating upward, 1.6 meters per second squared. Otis is still 6 kilograms. Keep in mind that the mass will not always be 6. This is just Otis in the problem. All the problems will change. Different objects have different mass, obviously. So question A is draw a free body diagram for this. Let's do that here. I'm going to draw a box, and remember this box represents Otis, not the elevator. Whoops. Okay, so let's look at all the forces on Otis. I always like to start with the gravitational force, which always points towards the center of the planet, or in other words, downwards in this case. Now, something is accelerating Otis up, which is the elevator. And so I want you to think what force is pushing or pulling Otis upward. You can pause and just think about it for a minute. Check your notes from the other day. And if you're thinking the tension force, that makes a lot of sense given that there is a cable here in the problem. But the cable is not touching Otis, is not pulling Otis directly. It is the elevator floor which pushes Otis up. And a floor is a surface, and it will be a normal force which pushes Otis up. And I purposefully drew that force, that arrow, larger than mg because there is an acceleration upward. Our free body diagram is done, and it is okay to do something like this. I do this all the time. I like to show that there is an acceleration upward, and that's why that force is larger. There is a net force on Otis, and so Otis will accelerate. That's Newton's second law. Now, be very careful with this. Don't draw that too close to the free body diagram. Technically, it kind of it's not part of the free body diagram. It's not really supposed to be there, but it's very useful to use it. So I like to do that, and I think it helps a lot of people when we write it that way. So let's do part B. The question was going to be, what is Fn? And we're going to use Newton's second law. Sum of all forces equals ma. We ask ourselves, is there acceleration? And in this case, yes, there is. So don't substitute right away. That's one thing I really recommend not to do in this situation. Don't substitute m or a yet. We should leave that for the end. Now we need to put our two forces in the equation. And now it matters. We want to go with the force that is in the direction of the acceleration. In other words, we want Fn first. We will subtract the other force mg, and we solve for Fn. Let's isolate Fn. This is mg plus ma. And now we can substitute. Mass of Otis is 6. Otis will not, or the object will not always be 6 kilograms. G, of course, is 10, as we wrote in our other notes previously. 6 again, and A is given to us over here. That's 1.6 meters per second squared. And if you type that in your calculator, it comes out to 69.6 newtons. It's always a good idea to go back in here, and this kind of ruins the free body diagram, but this is just for our own. We're just checking. 69.6 newtons versus 60 makes a lot of sense that the cat is accelerating upward. Cool, let's keep going. Is there anything else I need to say here? Keep in mind, mg is a force, ma is not a force. Just keep that in mind. Students in the past, they have mistaken mg for ma. They look similar because of the m. I'm trying to erase these. But they're not really the same at all. Just mathematically, they look similar. Okay, here's the next one. Otis is in a sling and is being accelerated downward. Okay. And I have the acceleration here as 0.4. Okay, so for part A, let's draw a free body diagram. Let's do it like this. Draw a box for Otis. Now, again, I would start with mg, gravitational force on Otis, and there is another force on Otis, which Otis is being held together in a sling, or in other words, a rope or a string, and that is definitely a tension force. Now, forgot to ask you to think about which way is the tension force pushing on Otis? And, well, I kind of gave it away. It's pulling up. You can only pull with ropes or strings. You cannot push with them. So the hand here cannot push downward on Otis with the string, can only pull up. And so we will label this as Ft for the tension. And so our question for part B is, what is the tension? So we'll go part B. Sum of all forces equals ma. Okay. Oh, by the way, I would like to show that there is a downward acceleration. It helps us to write our equation. We ask ourselves, is there acceleration? The answer is yes. So again, just leave it as ma. I would not start substituting numbers. We need to put the two forces, and we go with the force that is in the direction of A. This effectively ensures that we always get a positive answer here. Always, is that true? Well, for this problem, it's true. So we want to put mg first, and we want to subtract the ft. We want to isolate, we're trying to find ft, so I'm going to move ft to the other side, and then I'm going to subtract ma, so you should get mg minus ma equals ft. And now we can substitute. Mass of Otis is 6. Did I leave that there? Yep. G is 10 minus 6 the acceleration was 0.4. Okay, comes out to 57.6 newtons. It's okay to check to see if that makes sense. This is 60 newtons. That is 57.6 newtons. Yeah, the cat should accelerate downward. Forgot to mention um, how we can award points for this. So, yeah, I think I'll use this one as an example. You usually get a point for having the correct force here and the correct force here. You get a point for your equation. I must see it like this. Sum of all forces equals ma with no substitutions or anything. Um, sometimes it equals 0. Let's go back to the first one. So I don't even want to see it like this. I need to see this. Okay. If you substitute the forces, you would get a point for that, point for the answer, and a point for the units. In the case that the acceleration is 0, we would get a point for that as well. Okay, so 1, 2, 3, 4, 5, 6. About 6 or 7 points, something like that. Oh, and for this type of question, you would get a point for the third law pair of forces. Okay, let's keep going. Last question. Pushing Otis. So Otis is sleeping, and I couldn't draw a hand, so I drew a glove, but we're pushing Otis to the right. And let's see here. So Otis is 6 kilograms. Our pushing force is 29 newtons, and there is a friction force on Otis. So part A, let's draw a free body diagram. Otis, mg. The ground is pushing back up against Otis, Fn. Our pushing force is to the right, Fp, or F punch, as somebody said. Um, and there is a friction force. Now, the normal force is always perpendicular to the surface. So the normal force is always in that direction, perpendicular to the surface. Friction is along the surface. So is it left or right? Think about it for a moment. The friction wants to, not wants to, but the friction opposes slipping. So if Otis is going to slip to the right, the friction will be to the left. And we should actually make it a little bit shorter. If we're pushing Otis and Otis is moving or accelerating, which is implied here with part C, um, in other words, we need to have a rightward acceleration, and so Fp needs to be greater than Ff, the friction force. Okay, so clearly we have forces in 2 dimensions, the horizontal dimension and a vertical dimension. And so right away you want to write 2 Newton's second law equations. We'll make one vertical and we'll make one horizontal. Okay, so we'll start with the vertical one and we can separate these here. Now this is really important. We're just looking vertically. Look at the acceleration. Is the acceleration vertical at all? Right, and the answer is no. So when I ask, is there any acceleration vertically? Think about this situation. Is Otis accelerating up or down? No, no. So there is no acceleration. That's 0. So the sum of the vertical forces are 0, Does not matter which one we put first, but I think I usually put Fn first. Minus mg, Fn equals mg, adding mg to both sides. And we can answer part B here. Fn, of course, is 6 times g, which is 10. That's 10. Let's not do that. We'll just say this is 60 newtons. That's part B. Part C will be here. The horizontal forces. So clearly that acceleration is a horizontal acceleration, so we would say yes, there is an acceleration horizontally. And the only horizontal forces we want to include are Fp and Ff. We should put Fp first and subtract Ff. And you have to put both, you can't just leave them out. Okay. And we're asking for acceleration, so of course we will divide, let's just say we divide by m. Let me just rewrite all this. Fp minus Ff over m equals a. And we would just substitute the numbers. We have 29, minus 23.6 over the mass 6 will give us the acceleration of Otis. And this should come out to 0.9 meters per second squared is a. Okay, before we do the third law pair, I realize I forgot to say something very important. In the past, we've said to the right is positive, to the left is negative, up is positive, down is negative. And clearly here, we just threw all that out the window. So don't even think about that anymore. Um, by always putting the force that is greater first in the equation, we are keeping our answer here positive, and the direction is part of our drawing. It's kind of implied in the problem. We don't really worry about direction. We kind of know the direction. We're interested in getting a correct answer, getting a magnitude. That's what we really care about is the magnitude. So don't think right is positive, left is negative anymore. When we do kinematics, we should, but when we're dealing with forces, um, we kind of throw that out the window and we do something. We do it a little bit differently. Okay. So last one is D. Now look at the free body diagram again. Fn and mg are the same magnitude. Fn is 60, mg is 60. But again, those are not third law pairs. That's not two objects pushing on each other. This is the free body diagram is just Otis. So that won't work. We need two objects. And there's many of them here that you can say. We can do something similar to over here. Otis pushes downward on the floor. The floor pushes upward on Otis. Still applies here, right? Still applies here. So the floor is pushing on Otis with a 60 Newton force, and Otis pushes back downward on the floor with the same amount of force. So you could say that. I think I'll say, uh, yeah, I think I'll say the person, whoever, I guess that's us, person pushes right, rightward on Otis. And so Otis pushes, let's not say rightward, let's just say right, pushes left on person, or the hand, or whatever. Okay. Trying to move this. There we go. Okay. Person, Otis, right. Otis on the person is left. Okay. And there's more. There's other ways to do this. Um, if you take a look at the free body diagram, these forces all have a pair. It's not shown here, but they're all a pair. The floor puts a friction force on Otis, and Otis puts friction back on the floor, or puts a force back on the floor. Um, the Earth puts a gravitational force on Otis. Otis puts a gravitational force on the Earth. We should say direction there. The Earth puts a downward force on Otis. Otis puts a upward force on the Earth. Anyway, that's it for this lesson.